is rare, so you have to go far away to see one, right? Okay. Okay, so this is a plot where you can see frequency. You can see sensitivity curves that I think you discussed more or less the noise of one of these gravitational wave experiments. You were probably in your previous lecture, you were thinking of this, and LIGO, which is one of these curves. Okay, so this is just so that you can see the range of frequencies that these are ground-based observatories like LIGO and the future ones. And when we discuss the sources of noise, you will see why those ground-based experiments have a very hard time moving towards low frequency. This is LISA, future things. This is the pulsar timing arrays. These are some possible sources that we will describe a little bit more. And this is just the characteristic strain, the H of the gravitational wave that can be measured by these different experiments. And you can see that this, there's very different orders of magnitude in the strain that the pulsar timing arrays can observe, more like 10 to the minus 14 or something like that. And LIGO, which observes things, say, 10 to minus 21, right? So it's very different amplitude of the gravitational wave and also incredibly different frequencies, okay? So what I want to do in the next time is try to understand this curve for LIGO, and then today try to understand some of these sources and so on. Okay, so I will put this, I just cut and paste from some notes that I have, and I will put them in the website, but I did the cut and paste at the last minute because I'm afraid of this technology thing, so I just I was going to do the Blackboard, but when I saw the picture, I said, I don't know, this is too much for me. Okay, sorry about it. Okay, yeah? Yes?
Sensitivity curves for the PTAs, is there a difference between EPTA and IPTA just because of
I will go into some detail of how they work in like a couple. So we will see some estimates, and then you will see. But the number of pulsars and the length of time is it's starting. So okay. So I will not use the natural unit that Merdad is using. I will put G to 1 and C to 1 in these units. Mass and distance have the same units, right? So the Schwarzschild radius is 2m once you put G and C to 1, okay? I will use this. So, okay. Some things that you've already seen. I'm going to talk a lot about binaries. So there's two masses. There's the total mass. There's some sort of mass ratio, which this is some symmetric. This eta is a symmetric combination that gives you the mass ratio. The reduced mass that you already know in a binary system, and I will do all these estimates that I will do today with circular orbits, okay? And I will just do the Newtonian estimate, okay? So the binding energy, you already know, frequency from Kepler's law, okay? Omega is the angular frequency. So these are Newtonian formulas. In these formulas, there's no C, okay? So in these formulas, if you want to put back the dimensions, you don't need to put any C, okay? Oh, A, sorry, here. A is the semi-major axis, the separation in the binary, okay? So total mass, velocity, separation, angular frequency, any other symbol that I didn't say? No, I think it's okay. Okay, so first thing that I want to point to your attention is the fact that both LIGO and also LISA, so if I won't go back to the previous slide, but LIGO, if you have to think of a frequency, think 100 hertz. LISA, if you have to think of a frequency, think, I don't know, 10 to minus 2 hertz, something like this, okay? So the first point to make is about what kind of objects can produce sources for these experiments, okay? So as you know, or perhaps you know, perhaps you don't know, if you take stars and you look at their luminosity and their temperature, they lie on a very nice place in terms of luminosity and temperature called the main sequence of stars. The different stars, as you change the mass, these are small masses, big masses, they lie in some curve like this called the main sequence. And because luminosity, once you know the temperature and you know the luminosity, the flux is given by the sigma t to the fourth, and the luminosity is sigma t to the fourth times the radius of the star. So there are lines here that you can draw with given the luminosity and the temperature, you can figure out the size of the thing, right? Yeah, exactly. Yeah, HR diagram. Yes, thanks. Yeah. So it's a very nice empirical way to characterize stars, okay? And stars, they start their life in the main sequence, then later on they become giant, so they become much colder and much bigger. These are lines of constant size, the ones that are like this, and you can estimate this by these simple arguments. So what I've done in this plot is the following thing. Let's look at this plot. So first of all, you know, the binary is going around. It has a certain orbital period or orbital frequency, omega, I was calling. The gravitational waves, I will be assuming at the moment that there's just quadrupole radiation, right, which is the leading term. So the frequency of the gravitational waves, little f, is twice the orbital frequency. Okay? And then there's frequency and omega. So omega frequency, I will use 1 over the period, these frequencies, while these omegas is the omega that is 2 pi when you go around. So there might be some 2 pi's in the thing. Okay, so if you tell me a particular frequency, then you know the frequency of the gravitational waves, then you know the omegas, and then from this thing, if you know the mass, here I will take the examples of equal mass binaries, so to make it easy. You can, from here, you can know the radius of the binary, the separation of the two masses that, given the mass that they have, would be emitting at this particular frequency, right? And so what I plotted here is the line for LIGO, the line for LISA, okay, of what is the separation between the two stars in the binary in order to emit at this particular frequency, just from plugging this back in, okay? Very simple. So LISA, LIGO, LISA, okay? And then there's a bunch of other plots here, so points. For example, a neutron star lives here, okay? So this is the mass, roughly speaking, a mass and size of a neutron star, okay? This is in solar radius. This line, however, is the radius of stars as a function of mass when they live in the main sequence, okay? So you can see here that stars are much too big to be sources of gravitational radiation. So their sizes is like this. And if you wanted them to emit, say, for example, at the LIGO frequency or the LISA frequency, they need to be closer than the size of the stars, okay? So stars, regular stars, what they live their life, they cannot be sources for either LIGO or LISA by this very simple argument. You just cannot put them together. And it's even worse in the later times of the evolution of the stars when they become giants, much worse, okay? Yeah. Binary system of the two stars generate yes, yes. So what's happening is the two stars are going like that. The quadrupole is time dependent. The quadrupole of the system is time dependent. And so you create gravitational waves. As a result, you lose energy. And so the binary shrinks, and then they merge, LIGO, okay? Sees the merger. But if I want to discuss sources for LIGO and LISA, I cannot talk about orbiting stars. I need to talk about orbiting smaller things. This is where white dwarfs live. So white dwarfs can also not be a source for LIGO. So LIGO can only see neutron stars, and one of these lines here is the Schwarzschild radius of a black hole of this mass. So black holes, of course, are smaller, so black holes are fine, neutron stars are fine. The other one is this called last inner stable circular orbit. So if you have two masses, there's the last stable orbit for a circular one in a binary is a little bit, it's just a multiple of the Schwarzschild radius, right? So these two lines are the same. So conclusion from this plot, sources for LIGO and LISA have to be compact objects, either black holes, neutron stars, or white dwarfs, okay? Very simple estimate. Okay, furthermore, another thing to say is that if you have these two objects, even if so they are losing energy, they're coming together, and so the orbital period is shrinking, so the frequency is going up, until they merge, and they merge when they touch, right? When their size becomes the same as the separation, and so for any given object of a given mass, let's say two black holes, there will be a maximum frequency that you will emit because that's, you know. And so this is just a plot of this maximum frequency, which another way of getting something similar to the maximum frequency, you could take these formulas here and put, when they're going to merge, the velocity will be close to the speed of light, almost the speed of light. So you can get the orbital period for a total mass from the Kepler's law when V is of order C. That's if the thing is a black hole also, that's kind of, if not, it will be even before, right? If the thing is bigger, it will stop emitting even before. But for black holes, you can get something from there. Yeah. I'm doing all of these simple estimates, right? I will do. So, okay, so, and if you look like that, so if there's this is the line for black holes, let's say, the maximum frequency for a circular orbit, binaries of the same, two masses that are the same. So I simplified all these formulas, but of course you can keep, it's very simple. So this is the total mass, this is the maximum frequency with which you can possibly get with this total mass. This is the line, and this is the frequency range of LIGO and LISA, okay? And so this sets any objects that are too heavy, like for example, this guy, 2 10⁸ solar mass black holes. Their maximum frequency is even below anything in the LISA band. So these guys cannot be seen. Happens the same as the stars in the plot for LIGO, right? They're just too big. So this is a way for you to figure out what kind of sources are plausibly have a mass that is small enough that they can, before they touch, they can be in the bands of one of these experiments. The pulsar timing arrays is, outside of, outside of this. Okay, so let's now go to the, I'm sure you probably did this, let's do it again. So gravitational waves, I'm going to do quadrupole radiation, so the frequency is twice the orbital frequency. The strain that the gravitational wave produces, quadrupole formula, right? I'm just doing orders of magnitude. You can put all the 2 pi's and stuff. So second derivative of the quadrupole of the system divided by the distance. That's the strain that it produces at a distance d from the binary, okay? So so for the quadrupole moment, you have a mass which is of the size of the reduced mass that is, if one of them is big and the other one is small, the thing that is going around is something of the size of the, you can think of it that is going around, the small thing is going around, the big thing is in the center. So the quadrupole is of the size of the reduced mass, which is this, times the distance squared, that's the quadrupole, but you need the double dot, so that is the time derivative, which gives you the velocity, right? So the order of magnitude is reduced mass velocity squared divided by distance. And then you can play around with the Kepler's law to relate velocity with total mass and separation, and you can plug in whatever you want, okay? So, I've already, let's see. So I will use this formula a lot. V cubed, Kepler's law goes like this, okay? I will use this formula a lot. So in the thing before, here I can just, for the velocity, plug that in, and then you can have the strain then. So you can see that there's something with units of mass, okay? So strain is dimensionless. So you leave us I leave you as an exercise to see that this is actually a dimensionless thing. Well, you can, in this one is easy to see. Eta is dimensionless, V is dimensionless, mass and distance have the same units for me. Okay? So this is fine. And you can see now that the total mass and the this symmetric mass ratio combines in something we call the chirp mass. But in terms of the frequency, the strain scales as the frequency to the 2/3 and the distance, okay? So if you wanted to know how much power is how much energy is being lost by this binary, okay, what would you do? You know that the flux of gravitational waves is given by the h dot square, and you integrate in some surface around the binary. So pick some surface, and the flux is given by h dot square, and then area, okay? So the area of the surface will cancel this. So the power will be h dot square times the distance of this, pick the distance square. This distance square cancels with that one, and you plug it in, and you get this, okay? First of all, notice I forgot to say, power in these units is dimensionless, right? Because exercise, power is dimensionless. So this has to be a dimensionless quantity, and this is how it scales. So it goes as the velocity to the power 10, okay? So the amount of, and this you can trace the power 10, it's related to the fact that it's quadrupole radiation. Exercise, I don't know, dipole radiation, do the same. You will not get V to the 10. You will get something different. Okay, so, okay, but from here you can see that the power is much, much bigger towards the end than at the beginning, right? The V to the power 10, when you're near the merger and the velocities are close to the speed of light, this is just a huge power, right? So, equivalently, if you think about how much, okay, so this, okay, so, good. So yeah, let's do that. Now, if we can try to put the units back, okay? So this is dimensionless here, but there is something with the units of power, of energy per unit time, that you can construct with C and G. I leave you as an exercise to see what it is. You plug it back in, you get the actual formula, or, I mean, this is fine, but, and so let's give some examples, okay? So I will also put some notebook that I used to do all of these things. Again, I did cut and paste so that it was easy for me here. But, so the actual luminosity is C to the power 5, and G is the thing that gives you the units, okay? So these are some examples. So, oh, let me say something here before. So this is a dimensionless thing, right? Has no mass, okay? The mass is gone. There's their mass ratio. But so when two black holes merge, regardless of their mass, they produce the same luminosity when they are at the same speed, okay? Why is that, okay? Or in the total merger, you can think the amount of mass that is going to be radiated when the two black holes merge is a fraction of their rest mass. We will estimate that fraction of the rest mass, okay? So the bigger the black holes, it will be more energy, but the whole thing is going slower as well, okay? So those two factors cancel, and so the energy, let's say if you were to say, you know, when V is of order 1, you merge, the total power at that time is some constant of nature, this T to the 5th divided by G, times some correction because of this, which is not, you know, V, even if you put 0.5 to the power 10, is going to be smaller than than 1. So this number is smaller than 1. But this combination of what gives the units is c to the 5 g. This is some Planck energy or something, which is humongous. Okay, so that's something to remember. All the black hole mergers produce, a small fraction of this luminosity. Okay, but it's a humongous luminosity. So here are some examples of what this is in units of astronomers, ergs per second. So I have to give you the ergs per second units. Okay, it's 10 to the 59 ergs per second. You can compare this with other things, like the luminosity of the star of the sun is like 10 to the 33 ergs per second, right? So this is 22 orders of magnitude more than the luminosity of the sun. This c to the 5 divided by g. Okay, our galaxy has, I don't know, 10 to the 10 stars. So even one merger of two black holes, the luminosity is way more than the luminosity of the entire galaxy in the optical. Okay, and so this is related to the fact that you are converting a certain fraction of the rest mass when you merge. Okay, but the time is the fastest it can possibly be, because this is happening at the speed of light of the thing that is the smallest possible, a black hole, right? So the time scale, you're converting a small fraction of the speed of the rest mass in the shortest possible time scale possible, right? A star converts a small fraction of the rest mass of the hydrogen into helium when it burns, okay? But it takes age of, I don't know, like 10 to the 10 years, depends on the mass of the star by a big factor, but it can take billions of years for this energy to escape. So of course, the luminosity is much below, okay? But even if you try to compare with other sources of other astrophysical processes that are extreme, like for example, the accretion of mass into black holes that power quasars and so on, the typical luminosity of those things is something called the Eddington luminosity. I give you some formula here that you can put the numbers, but again, it's much, much smaller. So mergers of black holes are the most efficient thing possible at producing energy. They take a fair fraction of the rest mass in the shortest possible time possible, right? Because it's happening everything at the speed of light. Is okay? Any question? Okay. Okay, so now the question of the merger timescale that somebody asked me. Okay, so now how do we estimate the merger timescale? So I already estimated. So this I copied the Newtonian formula, power of the gravitational waves. This v to the 10 formula. Okay, how do I estimate how long it takes to merge? I can divide the binding energy of the system divided by the energy that is being radiated. It gives me a time scale. And this time scale now scales with v to the 8 because the energy goes like v squared, right? It's again super dependent on the velocity. Okay? So these are just examples. So of I take some total mass, and I fix the frequency. I say, okay, a source that LIGO can see, LISA can see, and so on. So I fix the frequency. So if I have the mass and I have the frequency of the gravitational wave, I have the orbital theory, I have the velocity, then I have everything for plugging into this formula. Okay, so this is just simple estimate of this time scale like that for various masses. Okay, I encourage you to just plug these things by yourself, okay? But this is, so, and here some line, like this one is 1 year, this is the age of the universe, okay? So first of all, something is going to merge by gravitational radiation. It better be that the time scale is less than the age of the universe, okay, so below. And if I'm going to see some change, let's say there's some system, I'm looking at it with one of these detectors. If I'm going to see something changing, it better be that this time scale is shorter than, say, 1 year or something like that. So for things that are below here, there's some chance of they will definitely merge before the age of the universe, but they will measure in a human time scale. I put a year that you can observe the merger, okay? Things between here and here, they merge in the age of the universe, but not in a human time scale, okay? So here's LIGO sources. LIGO sources definitely merge in the human time scale. We see the merger, and it's a small fraction of a second or something like this, depends on the mass, okay? LISA, some of the LISA sources live below, some of the LISA sources live above, depending on the mass. Some of them you can, and some of them they take too long. For pulsar timing arrays, some of them will merge in the age of the universe, some won't, but nothing happens in a human time scale. So a source for these pulsar timing arrays is going around, and for all practical purposes, the frequency is fixed, is not moving, is losing energy, but so slowly that in a human time scale we will never notice, okay? Yeah? I'm talking about the velocity of the two masses, one around the other. And the velocity, sorry? The light. The speed of light is it's constant, the speed of 1. I put it to 1 in this formula. So when you have to put units, I mean, not in the Newtonian formulas, there's no G, no C there, but in all of these other formulas, when you try to put the units back, you will see that you require some C's. That's why they're not showing up. If that's the question, they're not. C is not showing up because I put it to 1. Is that what you were asking, or something else? Yes. I'm not, when I said the speed of light, I'm talking about the order of magnitude of the speed of light, like 0.3 C or something like that. Like the easiest estimate for you to do is take these Newtonian formulas and plug the separation of this last stable circular orbit for a Schwarzschild black hole is like 3 times the Schwarzschild radius, and use that to use the Newtonian formulas to calculate the velocity at this moment. I mean, the formulas are not perfect because it's not Newtonian at this point, but you will see that the answer will give you of order the speed of light with a number which is smaller than 1 on the front, which is not too much small. So for me, once they are very close to each other, I'm calling it, for the purpose of this estimate, the speed of light, but it's like 0.3, something like this. Any other question? Yeah. Exactly. So let me step back. These pulsar timing arrays, we've just seen a signal. We don't know for a fact what is producing it. I believe, I don't know what other people believe. I believe most probably is the binaries of supermassive black hole binaries in the centers of the galaxies. Okay, very heavy black holes going around. What this plot shows you is that when they're going around, if they're at the separation in which the frequency or the period of the orbit is such that it would be, I don't know, 10 years or 5 years or something like that, so that they emit in the band of frequencies that the pulsar timing arrays can see. Yes, they are emitting gravitational waves, they're losing energy. Those gravitational waves are what produces what we see in the detector, but it's such a small fraction of energy is being lost that it takes a very long time for them to merge. If they're heavy enough, they would merge in the age of the universe, but never in like 10 years or something that these experiments last. So for the purpose of these experiments, there is a binary that's a fixed distance emitting at some rate. Okay? Yeah? I am ignoring the redshift. Yes. Redshift 0. Yeah. You will have to redshift if the thing is that, and indeed for the pulsar time, yeah. So for some examples, that's not a perfect thing. For LIGO, it's really pretty okay. for this estimate is okay. Yeah, right. Yeah. Let's see. Okay, another interesting. So astronomers and many times they talk about. So okay, let me go back. So as the binary goes around, okay, it loses energy, it shrinks, okay. The distance decreases, the velocity increases, everything goes together, all at least at the beginning while the Newtonian formulas are good, everything is following these formulas, right? So if you fix the velocity, say, that fixes the distance, the period, everything gets fixed. So what you can think of the distance changing slowly or the velocity increasing slowly, okay? So so it's just a one parameter thing where you say at what distance they are, or at what frequency are they emitting, and that is changing slowly. Okay, so so the power is one of these dimensionless numbers that you can think about. Another dimensionless number that people talk about is p dot, so the rate of change of the period. So if there were no gravitational waves being emitted, you know, this binary, let's say isolated with nothing in it, would be emitting always at the same with the same period. Okay, so there is a p dot, a change in the period because of the loss of energy due to gravitational waves, and p dot is a dimensionless number. Okay, because p is time, dot derivative, so with respect to time, so p dot is a dimensionless number, which is roughly speaking by how much does the period change in one period. Okay, so this is p dot. And these are just plots of p dot for you to take a look. The actual formula with all the 2 pi's and everything is this without the g's and the c's for the p dots. But this is just to tell, this again, I did the same thing. Put sources that I postulated are emitting at a given frequency. I give you the mass, I computed the p dot. Obviously, when p dot is order 1, it means merger, right? I'm changing the period in one period at the end, right? So LIGO gets to 1, so at the merger. But other things, depending on the mass, perhaps, but for pulsar timing arrays, never gets to 1 because they never merge, even in the age of the universe. So here, this is the age of the universe. Sorry, this is the maximum possible mass that you can have a black hole in the center. Anyway, okay. So this I think you already discussed, the binary pulsar. So this is an example of something doing the, you know, this binary is going around, is losing energy. As it loses energy, it's shrinking, and so the period is changing, and as a result of the period changing, the amount, so the pulsars emit pulses regularly. You count how many pulses you've received and how long that took you. If there's some prediction, if the orbit, you know, are always fixed, but you can see in so many orbits how much time it took, and because the period is shrinking, there's a deviation, and this deviation the equivalent of like 60 seconds in all of these decades of how long it should have taken to go around as many times as it went around the binary of the so the binary pulsar is 2 pulsars going around. Here are some of the parameters, okay, of so a third of a day is the period of this binary, but this period is changing. The p dot is very small, but over decades accumulates a total 60-second difference between how long it would have taken to give all of, it's going around every 0.3 days, so it went around many times in these many decades, okay? How much, but in each go around, in each period, the period only changed by 10 to the minus 12, but it accumulated enough that be 30 seconds or 60 seconds, whatever it is, and so you can see something, okay? So the p is changing, p dot is non-zero, but this I leave you as an exercise to show that for a constant p dot, this is just a Taylor expansion. That's why it's a parabola, okay? And the p double dot term, which will be the corrections to the parabola, very small, not visible, okay? This is just a parabola. The gravitational wave prediction is just about the size of this, the amplitude of this parabola. So the prediction for p dot. And you can do the prediction of p dot if you know the two masses and the separation of the binary, and also in this particular case, this eccentricity. So I also leave you as an exercise to take the formulas that I gave you that gives you p dot for a circular binary, estimate for the masses that are listed here, or find the masses, because in this table they are not the masses, but find the total mass, or the p, well, you have the period, estimate p dot. You will see it doesn't quite work out to 10 to minus 12 because of the eccentricity. You can also find those formulas. There are by now many pulsars for which something like this has been done, and you can estimate the p dot and the p dot that GR predicts, and pretty good. Any questions? No? But important thing, that's a parabola, just because this thing takes so long. This is the first correction in a Taylor expansion. If there was no p dot, the number, the time would be just linear with the period, right? The cycles versus time is just linear. That has been subtracted out, so the correction is a parabola. Yeah.
On the x-axis, what is the magnitude?
60, and this is seconds.
I don't know what the physical meaning.
The physical meaning is this thing went around a lot of times, right? So if the period had been fixed, you can calculate how long it should have taken for you to go around all these many periods. How many periods it went around? The period is a third of a day, right? P of the binary in days, 0.3. And this, I don't know how many decades, I don't know, 30 years or something. So it went around many times. So in all these many times, it should have taken, if the period was fixed, it should have taken so much, 30 years. But in reality, for this number of periods, it took a little bit less, okay? Because the period is getting shorter, because the gravitational waves, you're losing energy, so the period is getting shorter by how much? Wherever the p dot is here, 10 to the minus 12, okay? So that you can, and if you take 10 to the minus 12 over all this time, you will get the 60 seconds. Okay. Any other question? Yeah.
Binary system, you had other kinds of effects that produce orbital decay, right? For example, if it's supposed common under the binary, you have
Yes.
decay. In case of binary pulsar, you have another mechanism that also produces an orbital.
In this case, no, because it works with, and they're so close, right? But yes, in other, it depends on the distance, right? For example, in the LIGO sources, by the time they are just, is not, but you can imagine, for example, this is a very relevant question for supermassive black hole binaries, which are separated by quite a distance, like a parsec or a tenth of a parsec. And so maybe there's gas in the centers of galaxies, and maybe part of the loss of energy during some period of time is not given by gravitational radiation, but by something else. So in each case, in principle, you should try to think about all possible ways you could be losing energy, and they would all, if they are slow enough, they would lead to the same kind of thing, a shrinking of the orbit. But there would be other contributions to this p dot. Okay, so I have like 12:30. So let's see some other things. You can use this formula to try to estimate how the frequency of the binary evolves with time. I leave you as an exercise to fill out this piece and just integrate this equation to calculate the number of cycles as a function of time or frequency between one frequency and the other. Very simple to put it in. Okay, let me talk a little bit about the size of the gravitational wave signal, okay? So we already said, let's take an example in which, so the gravitational wave is, they are going around, they are emitting at some frequency. So roughly speaking, the gravitational wave is some cosine of omega t, okay, or 2 omega t because it's quadrupole radiation. But as the orbit is shrinking very slowly, this amplitude of the gravitational wave is what I estimated before, that as the frequency is changing, this amplitude is changing a little bit, okay? So this is more or less the shape of the strain of a binary as it evolves with time. For supermassive black hole binaries for the pulsar timing array, this doesn't change at all, as we were saying. For LIGO sources, it does change quite a bit during the merger, okay? Another thing that we are usually interested in is the Fourier transform of this to know the strain as a function of frequency. So just the regular Fourier transform of this h of t, right? And just as a reminder, you can see from the Fourier transform, this h of f has units of time, right? If I put it in the Fourier transform, h of t is dimensionless, and h of f has units of time, right? So if I want to do something dimensionless, I need to do something. For example, multiply by the frequency. Okay, so there's two options. For a pulsar timing array, this is like a constant. It is emitting at the constant frequency. So h of f is basically some sort of delta function. It's emitting only at one frequency with the amplitude h naught. For a chirping signal like the one in LIGO is changing with time, you have to be a little bit more careful of how you make the Fourier transform. So you can basically do the following thing. You can plug in here this h of f and try to do some stationary phase approximation. You probably discussed this in the other lecture, and you will get some h of f. Here are the steps for the stationary phase approximation. But roughly speaking, what you get is that the h of f scales in this way, okay? I leave you as an extra, plug this back in, do this, the stationary phase approximation and estimate h of f for a chirping signal. And when it's emitting at a given frequency, the order of magnitude is given by this, okay? You can check that this has the right units. h0 divided by f has units of time, okay? And there is a p dot there to the 1/2. And the reason why p dot enters here, I think is easy to understand. You can do the math, but the thing is changing its frequency, right? So in order to know the amplitude of the gravitational waves at a given frequency, you need to figure out how long this binary has spent in that. It's a chirping example. So the thing is changing its frequency. So depending on how much it spends in this frequency, what the amplitude of the gravitational waves are going to be. And the more it spends, the smaller the p dot, the bigger the h of f. And I think these formulas you already covered last time. So gravitational wave detectors have some source of noise. There's an h of f. And if I want to know how much signal to noise I will see some event, I would take the h of f of that event, divide by the noise in each of the frequencies, and sum that over all the frequencies, assuming the noise from this detector is stationary, so every frequency is independent, and so I get to add all the frequencies. And usually, as I was telling you, this h of f has units. This s of f have correspondingly units. This thing is dimensionless. So usually people in those plots, like the ones of the sensitivity curves that I was using, many times what they do is, first of all, they care about logs, how much signal to noise you get in each logarithmic interval of frequency, because we plot the x-axis in log, because it covers so many orders of magnitude. So you put df over f here, and you put various powers of the frequency to make all these things dimensionless. So f times s of f is a dimensionless quantity. F times h is dimensionless. So this is sometimes called the characteristic strain as a function of frequency, and that's some noise. And so the signal to noise is given by this. And okay, so And so when you plug into these formulas, when you plug these estimates for the for h of f, you get slightly different answers, okay? This one, only one frequency contributes, right? And while for here, all of the frequencies contribute. And when you plug in, and in here, there is some sort of delta function in frequency. The width of this delta function is the observing time. So when you plug delta of 0, you get observing time. And so as a result, when you do the signal to noise, oops, sorry. When you do the signal to noise for a monochromatic signal, this is what you get in terms of the amplitude of the. So the longer you observe, obviously the bigger the signal to noise. It scales with the time, and this is the scaling. And for a chirping signal, this is the contribution for to the signal to noise per each log of f. This is just by plugging in the formulas that I had before. Yes? The physical meaning of the noise is the following. So you are measuring h. Imagine the following thing, like LIGO at any given time. We will go into details of how it works, but at any given time, it will tell you the separation of the mirrors, okay? And it'll give you some number. This number has some error, okay? So even if there's no gravitational waves, there is a corresponding error that could look like a gravitational wave, okay? And this is, in a sense, the size of this error, okay, for each frequency. So the signal to noise is the size of the actual gravitational wave divided by the, of course, this noise is random, right? So you get to add the squares to get the signal to noise because it's a random variable. So this is the power spectrum of this noise. But this is the square, this f times s of f is the square of the typical gravitational wave signal that you would think is there even if there's nothing there, okay, from the noise of the measurement, okay? And this is the actual signal that is there, okay? Any other question? Yeah? The shape? Yeah, it's not a power law or anything like that. It's a very complicated function of which I will, oops. So it's this curve. Okay, this is the curve. Would be this f times h of f that I plotted before, and this is s times s of f, what I had in this. So square root, thanks. This is strain, not square. In the s of f is the square h of c square s. So this is, it has this shape. We will understand this shape whenever I do it, but it's not a power law. Okay. Okay, so now if we are here, we can try to think about strains of various sources. And here are just some examples for you to do of, I put two masses of this mass at a given distance, at given frequency. What's the strain? Plug it into the formula. But the thing to take away is the following thing. What are the distance? Of course, the strain is given also by the distance, how far away these things are, right? So now we have two options, basically. Either it's a source in our galaxy, so then distance is, say, 10 kiloparsecs, the size of our galaxy. Or is in if the rate is high enough that these things are happening in our galaxy all the time, there are many of them in our galaxy, then we will see them in our galaxy, and they would be at a distance of 10 kiloparsecs, will give us some signal. If there are not enough of them in our galaxy and we have to go far away and we have to go to faraway galaxies, then this brings the distance to much larger distances, right? So tens, hundreds of megaparsecs in order to accumulate, let's say if the rate has gone down, I need to accumulate enough galaxies to see this coming in. So, if you, depending on the masses and the frequencies, you can get lucky and it can be a source in our galaxy, and if not, it needs to be either much heavier, so the strain grows with the mass, right? So if I have to go further out, it needs to be heavier, okay? So these are just for you to get some sense. And at the end of the day, for the most part, for LIGO, we're always looking at external galaxies and far away, okay? And for LISA, there's options of white dwarf binaries in our own galaxy. At those separations relevant for LISA, even though they are very separated, the power is very small because they are going at the velocity very small with respect to the speed of light. They are so much closer that they can also emit similar to some LISA could see supermassive black holes far away or binary white dwarfs in our own galaxy. And you can plug those numbers, and one is solar mass for the white dwarfs, and the other one is 10 to the 5 solar masses for the supermassive black holes, but the distance takes it up for the okay. So these are examples of people going out there with surveys of stars and finding binary stars of white dwarfs. These are time, okay, the light curves where you can see the eclipses of the two stars. You can figure out so these are white dwarfs. You can figure out from the spectra what they are. You can figure out the period and you can estimate, from Gaia, you know where they are. You can estimate the strain. And these are surveys of specific binary white dwarfs in our own galaxy compared to the sensitivity curve of LISA. And you can see that individual white dwarf binaries in our own galaxy emit strong enough that, say, LISA could see them individually. Yes?
That road is a light card?
These are, yes, as a function of time, the flux that you receive from what looks like a single star, but they are two stars that are going around. They are eclipsing. When one goes in front of the other, you get less light. When the other one, you get this. You take the spectra. You can from there figure out what type of stars. You can see, and you can get constraints on the orbit from this and velocities from the spectra. And so you can figure out everything from there. You can estimate the strain that they can produce. You have all the parameters of the binaries. You can use the formulas that I had there. And this is this particular. I just took a random example to give you a sense. But I encourage you to plug in like numbers for a white dwarf if you want in our galaxy and see what. Yeah.
Is it possible to detect gravitational waves produced by cataclysmic variable stars?
I don't believe so. I mean, okay, with the experiments that I'm discussing here, I think we can try to estimate the strain from such things, but I don't think so. I don't think so. Okay, so I think I have what, 5 minutes, something like 10 minutes? Okay, 3 minutes. Yeah, with the question, I mean 10 minutes total with the question. Okay, so let's, what I want to discuss, the next thing that I want to discuss is cosmological background. So not gravitational waves from individual binaries, but from cosmological background. So it's slightly different topic. So I can stop here and you can ask me if there's more questions. I think it's a good time, or if not, I go. But yeah. Yes. Oh, in a monochromatic signal here. Yes. Yes, the reason I put it like this is so that you can see that that I didn't screw up with the dimensions. Okay, so the strain is the signal to noise ratio is a number. It's a dimensionless number. How much the signal divided by the noise, which both have the same number. So the strain is dimensionless. Obviously, the longer I can observe this signal with my detector, the biggest my signal to noise will be. So there's a time here. And this S of f is not dimensionless, the power spectrum of the gravitational waves. F times S of f is dimensionless. For the cosmologist, you know, when we do the CMB, we do microkelvin arc minutes. So the arc minute here gets translated to time. So in order to make it dimensionless, you need, you know, I mean, arc minute in the case of the CMB is dimensionless, so you can ignore all of this stuff. But, or the power spectrum for large-scale structure has units of megaparsec, right? So k cubed P of k is dimensionless. So here f times S of f is dimensionless. So this is the dimensionless noise, the equivalent of the k cubed P of k. This is dimensionless, and this is also dimensionless, frequency times time. So that's the reason. I wrote it like that, like this, but of course. Yeah? Yeah.
Can you, the next slide,
Yes?
the next one. Okay, the code of the right tab, yes. Is this the general relativity prediction?
These points are the general relativity predictions for the strain of the gravitational wave that Lisa would observe given the binary parameters, the masses, the separation, and so on, of this specific signal is this guy. And this is a paper, I took it from a paper describing that specific event, and they put into context other events that people have found. Not, you know, this is done with the Zwicky Transient Factory, which is surveying, I think, in the Palomar Observatory in California.
Thank you very much.
Yeah. Yeah. Can be, sorry. Yes. So gravitational waves behave for the purposes of their, in many ways, similar to light, right? So all of the gravitational effects that you associate when you talk about, say, the light from a distant source or the CMB, gravitational lensing, redshifts of various kinds, they all apply to gravitational waves. In addition to that, light can actually interact electromagnetically with stuff, which gravitational waves, if you estimate their interaction with, is very negligible. Maybe for some early universe things, no, but for this purpose, it's very negligible. So in that way, the universe is transparent, but every other thing like lensing or some gravitational potential difference between some place and some other place, all of it, Shapiro's time delay, all of this stuff applies, yeah. That's it? No more questions? Okay, I stop here and I'll continue from